Okay, hello everyone, dear students. So, wait for one last minute, then we are going to start. Okay, we are going to wait for one more minute, then we are going to start today's lecture. Okay, I guess we have waited enough time. Now we should start. Let me share. Before that, let me know you can hear me loud and clear. Please respond.
जी सर।
Okay, so in the last class lecture, we have seen memory organization and we have seen how these special temporal localities work, how actually cache memory tends to store values or memory portions on it. Okay, so we have seen memory hierarchy as well, and then what is memory hierarchy terminologies are we have seen this as well. That what is heat, what is mid. So anything is present in the upper level is heat or in the cache, and anything is absent in the cache is actually a miss. Okay, so we have seen this thing, and then we have seen hit rate, hit time, miss rate, miss penalty. We have seen these things. Then we have seen a memory organization, how we can actually, using direct map caching, how we can actually cover all these 32 RAM blocks within only 8 cache blocks. And we have seen that in the cache block, in the cache 8 block, we don't only store the tag bits, but also there is a valid bit and data as well, data memory. And in the valid bit, it is always yes, no, 0, 1, like this, one bit. Maybe one for yes, zero for no, like this, yes, no. And then there is that bit, then there is that data. Okay. Now it depends how much the cache can hold on the question. Like it is one word per block, and we have seen 4 words per block, 8 words per block examples as well. Okay. So we have seen 1, 4, 8 words per block examples. Today we are going to start with 2 words per block example and try to understand many things related to it. But before that, let me tell you one thing in here. I'm going to cover this slide, then I'm going to show you some pictures to understand how everything works in here. First thing, block size considerations. Okay, larger blocks should reduce miss rate. And what is miss rate? The amount of data or block is missing in the cache. So if the block size is larger, due to spatial locality, there will be more information, nearby informations together. The processor can demand them, and for that, there will be a reduced miss rate. Miss rate will be reduced. But if the size of the cache is fixed, if we increase the block size, like for example, here in this example, block size was 1 word per block. 1 word per block. Okay. So if we take 2 words per block, 4 words per block, then the block size is larger. So larger block size actually reduce the miss rate. But if the size of the cache is fixed, then if we increase the block size, if we take larger blocks, there will be fewer of them. The number of the blocks will be reduced. Like in here it is 8. Okay. For example, in 8 blocks we are covering 32 RAM blocks. 4 words per block. If we want to use 8 words per block, we have only 32 blocks in the RAM. Then the number of the cache block will reduce from 8 to 4. So larger blocks means if it is a fixed size cache, then block number will be less, fewer of them. It will increase more competition and it will increase the miss rate as well. So larger blocks will always not reduce the miss rate. If the cache size is fixed, then it will increase the miss rate due to larger miss penalty. Because if a block is missing, and if that block is larger, for example 8 words per block, then for a miss we have to copy 8 words. We have seen that in the last example, like what processor would do for missing word 20. We have seen processor have to copy 8 words into the cache, right? Please respond. So if the block size is larger, the miss penalty, the amount of time will be taken uh, to copy 8 words in the block will be much more bigger than copying only one word in the block. So if the block size is bigger, if there is a miss and we have to copy the entire block, if the block size is bigger, then it will take much more time to copy. So due to that, miss penalty will be larger. And this can override our benefit of reduced miss rate due to larger block. If the block size is larger, yes, we can get the reduced miss rate if the cache size is not fixed. Even if the cache size is not fixed, larger block rate should reduce the miss rate. But for any one miss, we have to copy uh, around like 8 words. If the block size is 8. So the miss penalty is larger. So this can override the benefit of reduced miss rate. So larger block is good, but not always. That is the main consideration in block size. Now I'm going back to the original thing that I'm going to show you with picture word files as well. Cache size. Okay. What is the size of the tag field? What is the size of the total cache in unit of bit? We are going to see these two things. But before that, remember now every information is 32-bit byte address. So everything in here is 32-bit byte address. What is this 32-bit? What is byte address? I'm going to show you now. And in direct map caching, we are going to find out the size of the tag field. Before that, let me tell you, now we have to use some formulas. To use some formulas, you have to represent the number of blocks and number of words per block in power of n, in power of 2. So cache size is 2 to the power n blocks. The cache size is now 2 to the power n blocks. Cache size was 8 blocks, now it is 2 to the power n blocks. If it is 2 to the power n instead of 2 to the power 3, remember, using the formula, cache size is for n blocks. Looking at this, can we not say in here n is equal to 3? Please respond
Yes, sir.
in this example. Okay, okay. So we know n is equal to 3. Now there is a here. Block size is 2 to the power n word. Block size. Okay, a block size. In first example that we have seen, the block 4 words per block, right? 2 to the power 2 blocks. Right? Now, Hello, can you hear me?
Yes, sir.
Hello, everyone. I think there is some internet connection problem in my end. Sorry for that. Now you can hear me properly?
ইয়েস স্যার
Yes,
এখন
sir.
শুনতে পাচ্ছি।
Yes, sir. Okay. So, have you seen that n is equal to 3? Up to now, everything is clear. Please respond.
Yes, sir.
Okay, so in the first example that we have seen, first let me know, have you seen this? The block size is 2 to the power n words. There are 2 to the power n blocks in the cache, and in every block, in every cache block or every index, there is 2 to the power m words available. 2 to the power m words. Now, in the first example that we have seen that there were actually 4 words per block. So, can we say it is 2 to the power 2 words per block? Please respond.
Yes, sir.
Okay, thank you. So, if it is represented in 2 to the power m, so can we say m is equal to, can we say that?
Yes, sir.
Okay. So, if the number of cache block is given and the number of words per block is given, can we find n and m? Can we find
Yes,
these two things?
yes, sir.
So we can find these two things if the number of blocks and number of words per block is given. Okay, why it is important to find n and m? Why it is important to find n and m? Again, the size is 32-bit byte address. Previously, processor was demanding word numbers, right? Please respond. Word addresses. Processor were demanding the word addresses. Please respond.
Yes, sir.
Now processor will demand in the mathematics byte addresses, not words, byte. Now if a processor demands byte addresses, what would happen? Let me show you in this picture. Can you see this picture? Please respond.
Yes, sir.
Okay, so cache size is 8 blocks, 2 words per block. New example, 2 words per block. 8 blocks in the cache and 2 words per block. And we know one word is equal to 4 byte is equal to 32 bit. We know this. Please respond. One word is equal to 4 byte and 32 bit.
Yes, sir.
Okay. So now the memory is byte addressable. Byte addressable. Now processor will not demand word number 18. It will demand byte number 18. And we have to find out where this byte number 18 lies in the memory. So we have to search for byte number 18, not the word number 18. Now the processor will demand the byte addresses. So all this example in direct map caching, we're going to see every memory with 32-bit and byte addresses. So how come we get to know which one is which byte? Let me tell you. Let me show you in here. Okay. So this example says cache size is 8 blocks. So 8 blocks 000 to 111. This is our cache index number 000 to 111. Okay. Now they are saying 2 words per block. So 2 words per block, what does it mean? Let me show you in this picture. So cache size is 8 blocks, 2 words per block. 2 words per block means there will be 2 words, 1, 2. So I have separated this line in here. Initially it was like this, empty. So 2 words per block means there will be actually 2 blocks in here. 2 blocks, 1, 2, 1, 2, 2 blocks for 2 words. Okay, so in a cache block there is 2 words, 1, 2. Now how we can name or index these two words. Remember, there were 8 cache blocks and we had to use 3 binary bits to name them or represent them individually. There is only 2 words. How many bits we are going to need to represent them differently, uniquely? One, yes. 1 bit is enough. This will be 0 number word. This will be 1 number word. Very good. Why 1? 2 to the power 0 is equal to 1. Because we have only actually 2 words in here. So 2 words per block means we need only 1 bit. 2 to the power 1 is 1. 2 to the power 1 is 2, so we need only 1 bit. Okay. As 2 to the power 3 is 8, so for 8 blocks we needed 3 bits. 2 to the power 1 is 2, so we need only 1 bit to represent each word. And out of this word, we know out of this each word we have 4 bytes. Now the memory is byte addressable. One word is equal to 4 bytes. So 4 bytes, each word has these 4 bytes. Now to index them in binary, how many bits we require for 4 bytes?
1.
2. Very good. 2 bits. 0 0 0 1 1 0 1 1. And this word is 0 number word. This word is 1 number word. Let me show you in this picture. So this is 0 number word. This is 1 number word. And this byte is 0 0 number byte. This byte is 1 number byte. This byte is 2 number byte. This byte is 3 number byte. Okay. So for example, our processor demands the 1 number byte. That is this byte, the 1 number byte. And how can we find this 1 number byte? First, we have to find in which block this 1 number byte is in, right? Please respond. Please respond.
Yes, sir.
To find out in which number block this byte is present, we have to take 3 bits of information, right? Please respond.
Yes, sir.
Okay. Then to find out in that block out of the 2 words in which word it is in, we have to actually use 1 more bit.
Yes, sir.
Okay. Then out of that word there are 4 bytes. And which byte it is exactly, we have to find out in 2 more bits. So can I say we need 3 plus 1 plus 2 bits to find out which byte it is, right?
Yes, sir.
So for number of cache blocks, it was 2 to the power 3. So selection bit is 3. For number of words, it was 2. So 2 to the power 1, the selection bit is 1 from here. And every time each word will have 4 bytes. It will be fixed. Always 2 bits, selection bits required to find out which byte it is. Okay, which byte it is. Now, let me tell you. To find out exact byte, we need 3 plus 1 plus 2, 6 bits. Can I say this is n, this is m, this is 2. So it is n plus m plus 2. Remember, number of cache block is 2 to the power n. So for this example, n is 3, right? Please respond.
Yes, sir.
For this example,
Yes,
2
sir.
to the power m words, 2 to the power m words, m is equal to 1. Please respond. Some noise is coming from whose mic? Okay. Okay, no more noises. So if the block size is 2 to the power m word, so m is equal to 1 in here, right? Please respond. M is equal to 1.
Yes, sir.
So then can we say to find the exact byte, we need n plus m plus 2 bytes. So can we say to find out which byte it is, we need n plus m plus 2 bytes, 2 bits, sorry. This is the selection bit. Is it clear? Please respond n plus m plus 2. Is it clear?
Yes, sir.
Yes, sir.
So now our assumptions are like this. If cache block is equal to 2 to the power n number of per, per block is equal to 2 to the power m, then to find the exact byte we need n plus m plus 2 bits. Please respond.
Yes, sir.
So
Yes, sir.
if the cache block number is given, like cache block is 8, number of words is, for example, 2, can we not find the selection bit is actually 3 plus 1 plus 2, which is 6? Is the response?
Yes, sir.
Sir, m
If
equal
these
to
two,
2 আর কথা ছিল?
what?
M equal to
No, number of words per block is 2. So it means it is actually 2 to the power 1. So what is m?
yes, sir, yes, sir. বুঝতে
M is
পারছি।
1.
Yes, sir. M equal to 1.
Yes, here n is equal to 3.
Yes, sir.
Okay, okay. And I have said it is 32-bit byte address. Remember one more thing. 32 bits byte address, 32-bit address. So in here, to find out the index and tag, what we have used, again noise coming from someone's mic. Hasan sound noise is coming from your mic. I have to mute you again.
স্যার উনি হয়তো কিছু বলতে চাইছিলেন।
You have to say, if you have to say something Hasan sound, write it down in the chat box because we cannot hear you. We can only hear the noise. So if you write it down in the chat box, I'll read it and answer you. So now, if I can say, what is the tag bit? What is the tag bit? Okay, what is the tag bit? And what was that? This was block number, right? In which block that word was going, right? Please respond.
Yes, sir.
Yes, sir.
In this example, we find out the last 3 bit, the indexing bit was to find out or select which block it was going, right? So it is, we can say that it was selection bit. The index was actually the selection bit. So can we say tag is equal to sorry, total bit minus the selection bit? For example, in here, in this example, total bit was 5 and selection bit was 3. So it was 2, the tag bit. Can we say tag bit is total bit minus selection bit? Can we say that?
Yes, sir.
So if the tag bit is total bit minus selection bit, in this example, 32-bit byte address, 32-bit byte address, in this example, the memory is total 32-bit. Can we say the tag bit is equal to 32 minus n plus m plus 2. Can I say that the formula of tag should be 32 minus the selection bit? Please respond.
Yes, sir.
So this is it, the formula. Now clear everyone, please respond.
Yes, sir.
Okay, so this was very simple topic. Now I'm moving to the next topic quickly. Okay.
Sir,
Yes,
should
yes.
not the N be tag bits?
But
Tag bit দিয়ে স্যার আমরা ব্লক আইডেন্টিফাই করি, রাইট?
no, no. Block is identified with the index in which block it is going, not the tag bit.
জি স্যার, বুঝতে পারছি।
Now clear everyone, please respond.
Yes, sir.
Okay, fine. So going to the next topics, and I'm going to be a little bit quick in here, and you have to hurry to respond to me as well so that we can move faster. Okay, we have plenty of topics to cover. So now in 32-bit byte address, again same examples again. What is the size of the cache? Total size of the cache in unit of bit. Let me take you back in here. So can I say the size of the tag, size of the total cache is the total size of this? Right? Please respond. Because these are only the index numbers and this is inside the cache, valid bit, tag bit, data. So if we can add all this, we are going to get the total size of the cache in number of bits, right? Please respond.
Yes, sir.
Yes, sir.
Okay, so can we say valid bit is only one bit because it is yes and no, one or zero? We can add design that with only bit, only one bit. So it is only one bit, right?
Yes,
So
sir.
for valid bit, I'm going to find out the total size of the cache. Now, if I can find out the total size of one index and multiply it with the number of index like 8, I'm going to get the total size, right? আমি যদি একটা ইন্ডেক্সের টোটাল সাইজ বের করতে পারি এই তিনটাকে যোগ করে ভ্যালিড ট্যাগ আর ডেটাকে যোগ করে একটা ইন্ডেক্সের টোটাল সাইজ বের করতে পারি এবং সেটাকে যদি আমি নাম্বার অফ ব্লকস ইন দা ক্যাশ দিয়ে গুণ দেই তাহলে কি টোটাল সাইজ পাবো না ক্যাশের?
জি স্যার।
ওকে,
Yes, sir.
so I think I'm very clear to all of you. So I have to only find out the total size of a single index, then I'm going to multiply it with the number of blocks in the cache. Okay, so you guys are going to say what it will be. Valid bit will be 1, right? Now I'm going to find out the size of the cache.
স্যার নাম্বার অফ ব্লকস এটা ফিক্স না, সবসময় তো 8টাই ব্লকস থাকে।
No. You are going to see some examples today. There will be more than 512 plus sections. Okay, so see that size of the cache, we are going to find out how. We are going to find out the size of one index and multiply it with the number of blocks in the cache. So if I can add all this size in unit of bit, remember we have to find the size in unit of bit, not in byte, not in words, but in bits. Okay, so if I can add this, valid bit will be only one bit, right? Please respond.
Yes, sir.
Okay, so 1 for valid bit. Now plus. Now for tag, it is this. Please respond.
Yes, sir.
Valid plus tag. Valid plus tag. Okay. Now we have to find out the data. Now this is a little bit tricky, but really interesting. How many? What is the size of the data will be? Okay. First, let me tell you, if we can find out the number of words in here, because the number of words actually can be different for multiple examples, like 1 word per block, 2 words per block, 4, 8 words per block. So if we can find out the number of words per block, and if we represent their size in number of bits, it is the total size of the data. আমরা যদি এখানে জানতে পারি কয়টা ওয়ার্ড আছে এবং সেটাকে যদি নাম্বার অফ বিট এ রিপ্রেজেন্ট করতে পারি তাহলেই সেটা ডেটার সাইজ, রাইট? প্লিজ রেসপন্ড।
Yes, sir.
ওকে,
স্যার বিট নাকি বাইটে নিতে হবে?
বিট বিট বিট। So for data, if I say, for data, if I say the number of words is actually 2 to the power m, is it clear? Please respond. Please respond.
Yes, sir.
And if I can remember, this is 2 to the power m, we are adding the data size in here, okay? So 2 to the power n is the number of words. If we multiply this with 32, we are going to get the total size in number of bits, because one word is equal to 32 bits. Please respond.
Yes, sir.
Okay, so if we add all this now, if we add all these informations, this is the size of a single index, right?
Yes, sir.
If we can multiply this with the number of blocks in the cache, we are going to get the total size of the cache.
Yes, sir.
Clear everyone? Formula, let me show you. This 32 is represented as 8 into 4. 8 into 4 in this formula, let me show you. So no 32, 2 to the power m into 32, 32 minus n plus m plus 2. So this is data, this is tag, this is valid bit multiplied with number of blocks in the cache. And if the number of blocks and number of words are given, we can find out n and m value as well to find out the total size of the cache in unit of bit as well, right? Please respond.
Yes, sir.
Whenever you have to find out the number of bits, size of the cache, never find the exact value. Write the formula, replace this n and m with the values of it. Okay? Never try to find out the original value. Just replace n and m with their original value. And keep it like this. You are going to get full mark. If you try to find out the full value, if you mistakenly miscalculate and get the result wrong, you are going to get 0. So do not try to be too much smart to find out the value. Just keep it like simple like this. Just replace n and m with the original value. That will be all needed. So I guess there is no confusion in that part. I'm moving to the next slide quickly. Now, previously a processor was demanding number of words, 18 number words, find out that word for me. Now processor is demanding different things, bytes. Okay, so where does this 1200 number byte will go? In which block it will go? Now, if processor demands 1200 number byte, actually that is not the question. What is processor is demanding? Question is in which block it will go. Like the question is simple in here. We are not asking what will happen for processor demanding 18 number word. We are asking where it will go. Your answer should be simple. Cache block number 010. The question is simple in here. In which block 1200 number byte will go? In which block 1200 number byte will go? To find out, we have to use this formula. Two things. First, block address, then block number. Remember the block address, if we want to find out the block address, we need to know how many words per block is in there. Okay, in this example, there is 64 blocks. Now, first different example. In every example, we had 8 cache blocks. Now it is different. 64 blocks. Now we have 64 blocks in the cache. Now we have 16 bytes per block. Can you please tell me, looking at this, how many words per block?
4.
4.
Four.
Very good. 4. So if the question is like 64 blocks, 4 words per block, and it is if the question is like 64 blocks, 16 bytes per block, both are same. Now to find out in which block 1200 number byte will go, we have to find out the block address first, then the block number. block address is the floor. Remember, we know ceiling floor, we know this. The floor of 1200 divided by the number of bytes present per block. If the question was like 4 words per block, still we have to divide it by 16 because there is 16 bytes per block. So we are going to take floor of the number byte divided by the amount of bytes per block. So this is 75 point something. If we take floor, it will be 75. Even it is 75.99999, we are going to take 75. Is it clear? Please respond.
Yes, sir.
Then the block number will be 75 mod 64. 75 mod 64. And we do know how to find out the modulus result as well, right? You do know that? The remainder, modulus is the remainder after dividing 75 by 64. Is it clear or not? Please respond.
Yes, sir.
Yes, sir.
Okay, in case you don't know how to find the modulus, let me know before in the exam. If you make mistakes, I'm going to decrease your mark, reduce your mark. Okay, you cannot make mistakes in here. Okay, because if you make one mistake in here, entire calculation of the mathematics will be wrong. So do not make simple mistakes in here. Okay. Now looking at this, if we have to design the memory field consists of tag, index, offset. Remember, this index plus offset is the selection bit. Let me tell you, I have shown you that index is the selection bit, but actually the selection bit is actually index plus offset. Let me tell you, in here, the main selection bit is actually index plus offset. Index is n. Remember, index is n. Offset is n plus 2, the rest in this selection bit. Index plus offset. Remember, offset is always n plus 2. Index is n. Selection bit is index plus offset. Where index is only n, offset is n plus 2. Okay, back in here. Okay, so what is the total bit? Total amount of bit. If we see this formula, total bit minus index is equal to tag. So total bit will be tag plus index, right? Or sorry, tag plus selection bit. The total memory field, let me tell you, total memory field will be tag plus selection bit. Right? Please respond.
Yes, sir.
So it will be, I can say, tag plus index plus offset. Can I say that? Please respond.
Yes,
Because
sir.
selection bit is index plus offset. The total memory field is tag, index, offset. Combination of these three will be 32 bits. As you can say 22, 6, 4. But how this is 22, how this is 6, how this is 4. In here, there were 64 blocks. So 2 to the power 6 blocks, right? Number of blocks 2 to the power 6.
Yes, sir.
So n is 6, index is 6. And there were 16 bytes per block. 16 bytes means 4 words per block. 4 words mean 2 to the power 2. So offset is m plus 2. So if m is equal to 2, offset will be 4. Let me tell you again, show you 4 words per block means 2 to the power m words per block. So m in here, m is equal to 2. So offset is always m plus 2. Will be 2 plus 2 is equal to 4. Offset is 4. Okay. If we look at offset is equal to 4, we can still say there are 16 bytes in the block or 4 words in the block. How? Because offset is m plus 2. So m will be 2. and index is 6, and tag is total 32 minus index plus offset, so it will be 22 bits. And if we name them, this is from 0 to 3, 4 to 9, 10 to 31 bits in here. Okay, clear? Even if this field is given, like offset is 0 to 3, index is 4 to 9, tag is 10 to 31, looking at this, we can say what the answer will be. Like how many words in there in the cache? 4 words or 16 byte. How? Offset is 0 to 3, 4 bits. So offset is m plus 2. So m will be 2. 2 to the power 2 is 4. And how many entries does cache have? 64 blocks. How? Index is 4 to 6, 4 to 9. So 4, 5, 6, 7, 8, 9, 6 bits. 2 to the power 6 is equal to 64. So this is vice versa. From this mathematics, this field we can design. From given that field, we can design these questions as well. How many words, how many blocks are there, you can find out as well. Now we are going to see 2 examples in here. This will be a long class, so concentrate. Suppose you are required to design a 512 kilobyte cache with 4 words data per block. Each word contains 4 bytes of data. We know that there are 32 bits in the memory. We do know that as well. Calculate the number of blocks in the cache, find out the number of index bit and tag bits, calculate the actual size of the cache. Okay. We have 512 kilobyte data in here, and we have 4 words per block. To find out the number of blocks, we have to divide this 512 kilobyte with 4 words. So to find out the solution of A, we have to divide 512 by 4 words. But unfortunately, if we want to divide this, like going to divide these 4 words, these two are not in same unit, right? Please respond. One is
Yes,
in
sir.
kilobyte and one is in word. So we have to take it in same amount in maybe in byte, only in byte. Okay. As the memory is byte addressable, we are going to take them in byte. So 512 into, as a 1 kilobyte is 2 to the power, let me show you, 10 bytes. 1 kilobyte is equal to 2 to the power 10 bytes. Okay, so I'm going to do is multiply this is 2 to the power 10. So this is 512 into 2 to the power 10. And we can represent 512 in 2 to the power 2 as well. 2 to the power 9 is 512. And we have to divide this with 4 words. And 4 words means 2 to the power 2 words, right? Please respond.
Yes, sir.
Yes,
And
sir.
every word is how many bytes? 4 byte.
Yes, sir.
Yes, sir.
So every word is 4 byte, and that is 2 to the power 2 as well. So if we do find out the result of the calculation, the result will be 2 to the power 15. At the top, it is actually 2 to the power 19, you can say, divided by 2 to the power 4, will be 2 to the power 15. So the number of blocks is 2 to the power 15. Now looking at this 2 to the power 15, what is the value of n? 15, right? N, number of blocks, 2 to the power n, n is equal to 15. So if n is equal to 15, index is 15. Remember, n is actually index in here. Index is 15. And if we want to find out the tag bits, we need to use the formula. What is the formula of the tag bit? Can you please tell me? So can you please tell me what will be the tag bits in here? What will be the tag bits? Because we have to find out the tag bits.
So 6.
How 6?
Oh no, sorry.
32 minus.
Just 6.
You have to say how it is 6. Can you not say how it is 6? How it is what? Is it 6 or what? Tag bits will be 13. Okay? Clear? Everyone, please respond
Yes, sir.
using the formula. Okay. Now calculate the actual size. Calculate the actual size. We know the formula. Just replace this formula n and m with 15 is equal to n every time 15, 15 and m is equal to 2, 2. Can we do this? Just replace this with n and m.
Yes, sir.
Okay, and this is the solution for the first one. 2 to the power 15, index is 15, tag bit is 13, and the solution is 2 to the power 15 into 1, that is the valid bit, plus 13 plus 4 into 4. Doesn't matter, just represent it like whatever is in there in the power of 2. Do not try to find out the value. If you try to find out and if you make mistake, do not ask for any partial mark, because there would be only 1 or 2 mark in here and there will be no partial for that. Just use the formula, replace nm with the value of nm. Just this. Now next big mathematics. After that we have one more mathematics and few theories as well to finish the slide in here. A long topic but not boring. I guess you are finding it really interesting as this is mathematics, not theories. Suppose you have designed 256 kilobyte cache is 2 words data per block. Now processor demands these bytes 12, 42, 7, 15, 40, 39. We have to find out which one is hit, which one is miss, and you have one assignment done. This is your next home assignment. B and C. This is your next home assignment. You have to submit within the next week. So before that was first let me show you this solution. 256 kilobyte, 2 words data per block. Can we find the number of blocks in here? Let me show you. 256 is 2 to the power 8 and into 2 to the power 10 to take it to byte, and 2 words into 4, which is 4 byte. Every word is 4 bytes. So 2 into 2 to the power 2, it is 2 to the power 15 again. 2 to the power 15 again. So now we know the number of blocks in here. We have to learn something as well in here, and that is this formula. Block copied from this to this. Okay, I'm going to write it in here, and you are going to just take note of this. Please write down all of this in here in your paper. Block copied from block address BA into number of bytes minus block address into number of bytes plus number of bytes minus 1. Can you please copy that on your paper? I'm going to give you 2 minutes for this. Remember, this is block address into number of bytes minus block address into number of bytes plus number of bytes minus 1. Okay, copy it like this. Because we are going to need this so often. Is it clear?
স্যার
Copied?
প্রথমটা কি ইনটু
Into multiplied, yes. Into, here is into as well. Multiplied, multiplied. Clear, everyone? Can I close this one?
Yes, sir.
Okay, going back to the slide. Now we have to find out whether 12 is hit or miss, because we have to find out the hit rate, miss rate. Miss rate actually. We have to calculate the miss rate for this memory addresses, this memory address accesses. 12, 42, 7, 15, 40, 39. Memory is byte addressable. Now, back in here. For 12, where this 12 number byte will go, we have to find out in this way. First block address, then block number. Block address is the number divided by number of bytes per block. Then block number is that block address mod the number of blocks in the cache. So we're going to follow this. So 12 block address will be floor of 12 divided by 8. Why divided by 8? Because there was only 2 words, so 8 bytes. 2 words means 8 bytes. So 12 divided by 8 will be 1. If we take the floor, then block number will be block address mod number of blocks. So block address is actually 1. Number of bytes actually per block. No. It will be number of blocks. Yes. So it is block address 1 mod number of blocks, which is 2 to the power 15. So 1 mod 2 to the power 15 is 1. Now we have to find out how many bytes will be copied for this only missing 12, because 12 is missed. Initially 12 is not in the cache, so 12 will be missed. But for 12, which one will be there in the memory? Which one will be there in the memory? 8 to 15. How? Using this formula. Let me show you how it is using this formula in here. Okay, so in here, block address is 1, right? Please respond. Please respond.
Yes, sir.
Yes, sir.
1 into number of bytes, which is 8. Number of bytes per block, which is 8.
Yes,
Yes,
sir.
sir.
So 1 into 8 will be 8, right?
Yes, sir.
Then 2, what? 8 to 15. How this is 15? Again, block address into number of bytes. Block address into number of bytes. It will be 8 plus number of bytes minus 1. Number of bytes is 8 minus 1 is 7. So 8 plus 7 will be 15. So it is 8 to 15. Now why this is important to find out what will be the number of uh, bytes copied. Why this is really important to find out which address is being copied now. This is important because if next time processor demands anything in between that range from 8 to 15, it will be a hit. Like for 15, it will be a hit. Now, as it is in the memory, because we have copied this complete address to the cache, anything present in the cache will be hit. So anything comes in between 12 to 8 to 15 will be hit now, because for 12 we have copied this. Now for 42, okay. For 42, what will happen? Again, 42 divided 8, it is 5. Block number will be 5 mod 2 to the power 15 will be 5. Number of address copied will be 40 to 47. 40 to 47. Then it has miss as well, because there is no 42, 42, 47 or 42 in the memory. So it has miss. Now, can you explain this to me? For 7, it is miss. For 7, we copy from 0 to 7. That is miss. Okay. If we find out the block number, block address, we'll be able to see for 7 it is miss. Can you please tell me why these two are hit?
Because 12 got this from the
15 was in here from this copy, and this 40 hit is because of this memory copy, right? Please respond.
Yes, sir.
Okay, because of that, these two are hit and these two are not in the memory, so these two were missed. So out of the 6, 4 was missed, so miss rate is 4 by 6, right? Please respond.
Yes, sir.
So we had to calculate the miss rate for the following memory address, and we have calculated successfully. What we have to find out, two things similar to this slide in here: block address, block number, block address, block number. Then one thing, using that formula from that picture, using that formula, we have to find out the number of bytes copied for this only one miss, because it is really important. Next time anything comes in between this range, it will be a hit, because now it is in the memory. Okay, so everyone clear about this math? Please respond.
ইয়েস স্যার।
Clear everyone? So
স্যার
assignment
স্লাইডে
is,
ওই
let me,
ফর্মুলাটা দেওয়া যায় না
what?
স্যার? স্লাইডে ওই ফর্মুলাটা লিখে দিলে স্যার ভালো হতো।
You haven't written that in your
জি
paper?
স্যার লিখছি স্যার,
So
কিন্তু
can you
স্লাইড
please type it for me? Okay, let me include this in the slide. Okay. Even if I include this, that slide is not uploaded. Let me write it down and give it to you in the chat box. Okay. So the formula is actually block address into number of bytes. Sorry, byte. This is, sorry, from these two. Is plus sorry, here from this range to this range. Okay. So we have to find out from which to what has been copied. Okay. I'm going to drop this formula in the chat box as well. So we have that formula in the chat box. So okay, formula is given. Similar formula, block address into number of bytes, to block address into number of bytes plus number of bytes minus one. Just this formula. Okay. Okay, so I have dropped that in the chat box, and I'm going to say what is the assignment is. You have done this same mathematics for 2 words. You have to do it for 4 words, and you have to find out the miss rate. Just the difference is now it is 4 words per block. Okay, and then in the question number C, I'm not going to give you the answer until you finish submitting the assignment, because this is your assignment. I'm not going to give you answer of your assignment. You have to do it on your own. Okay. There will be change in the miss rate, because in this example miss rate is 4/6. In the question number B, the miss rate will not be 4/6, will be something else. You have to decide why the change of the miss rate happened and due to which principle of locality. It could be both temporal spatial, or could be none, or could be temporal, could be spatial. What is that answer? You have to find out in here. Why there is change in the miss rate from A to B, you have to explain in here. And for which principle of locality? We have seen two locality, temporal, spatial. For which principle of locality it happened? You have to find out. Clear, everyone? Could be none, could be both, could be any of the two. You have to find out. So this is your assignment, question B and C. Now, few parts remains of this lecture. I'm going to go through clearly. Write miss and actually write through policy and write back policy, two policies. Write through policy is writing from cache to memory. Simple things, cache to memory. Okay, it is slow. Every write eventually gets to memory. So it is cache to memory. write through policy is cache to memory, cache to RAM. Memory is RAM, cache is cache memory. So cache to memory. Okay. And what is write back policy? It is from memory to cache. The reverse one. It is cache to memory. It is memory to cache. Write only to cache from the memory. Then write cache block back to the memory when evict block from cache. Okay, write back policy. Write back policy, we are going to write only to the cache. Okay, so we are going to take some portion of the memory from the RAM to write it on the cache. Then if there is some empty space in the cache, for that we are going to write back to the memory as well. Let me explain this again in Bengali. Write back policy is we are going to write to the cache. Okay, we are going to write to the cache and write cache block back to memory when evict block from cache. For example, I have 8 blocks in the cache. Okay, let me again explain you. আমাদের কাছে 8টা ব্লক আছে ক্যাশের মধ্যে। রাইট ব্যাক পলিসিটা হচ্ছে, ফর এক্সাম্পল আমার নতুন কোনো ওয়ার্ড আসলো যেটা রিপ্লেস করে দিবে কোনো একটা ব্লককে। যেই ব্লকটা রিপ্লেস হয়ে যাবে সেই ব্লকটাকে আবার মেমোরিতে আমরা ব্যাকও করে দিব। Yes, write back policy is only write to cache, but after writing we have to return the block which is going to be evicted. যে ব্লকটাকে তুলে নেওয়া হবে রিপ্লেস করার জন্য, that block will be returned back to the memory or RAM. Okay, so this is whenever there is a write in the cache, the dirty bit is 1. There is a dirty bit for every cache block. If there is no, like the valid bit, there is a dirty bit as well. If there is anything going to be written in the cache, so dirty bit will be 1. Otherwise, it is initially 0. And one last mathematics before I end today's lecture. Actually, 2. Very simple. Very simple. I will take only 5 minutes to discuss this. I cache miss rate, instruction cache miss rate, data cache miss rate. If these things are given in the question. For example, if I say I cache miss rate is the miss rate from question number A and data cache miss rating is the question number B, like this. So this could be a second part of a huge mathematics. Okay, this mathematics can be second part of the big mathematics. Miss penalty will be given, base CPI ideal cache for ideal cache will be given, load and storage percentages will be given as well. What we have to do, we have to find out miss CPI, miss cycle per instruction, and actual CPI. 2 things. We need to find out 2 things. You are going to be given all these values. Maybe you are going to find that value in some question number A, find that value, that miss rate in question number B. Then you will be given these 3 values and you are going to be asked to find out the miss cycle per instruction and actual CPI. So miss cycle per instruction will be separate for all the miss rates in here. Like for I cache, it will be 2%, which is 0.02 into miss penalty, miss cycle per instruction. And for D cache, it will be miss rate into miss penalty. And the load and store are related to data, so it will go to the data as well. So in the data cache, remember, only in the data cache we are going to multiply the load and storage percentages as well. Normally the miss CPI is miss rate into miss penalty. Let me tell you the formula. Normally it is miss rate into penalty. Normally the formula is like this: miss rate into miss penalty. Miss rate you are going to be given in the question, miss penalty will be given in the question. You have to find out miss rate into miss penalty. Only for data cache, if the load and stores are given, you are going to multiply that. So it is simple. Please respond.
Yes, sir.
Okay, and you have to find out the actual CPI. Actual CPI will be we have to, for example, if there was no miss rate, no miss, at least we needed 2 cycle per instruction. Due to the misses, we need this amount of more cycles. Remember, ideal cache means there is no miss rate. So even if there is no miss rate, the base CPI is 2. So we need 2 at least for this if there is no miss. So what will be the total CPI or actual CPI? Total CPI will be 2 plus this 2 plus 1.44. So it will be 5.4. And how the ideal CPI is faster than actual? If we divide 5.44 by these two, 5.44 divide these two, we are going to get ideal CPI was actually 2.72 times faster. But because of the miss rate, we need extra extra 3.44 actually cycle per instruction. Now another math, very simple math, average memory access time. Okay, last math of the slide of this course, average memory access time, AMAT. You will be given the hit time, you will be given the miss rate, you will be given the miss penalty. You just have to calculate. Maybe the miss rate will be coming from some question number A, some question number B. So if you calculate that perfectly, you are going to calculate this perfectly. Okay. So it is related to the previous math, like the example we have seen. This could be another sub part of a big mathematics where you are going to find out the miss rate. So after you find out the miss rate, you are going to find out this formula, average memory access time, hit time plus miss rate into miss penalty. Hit time is 1 nanosecond, 1 cycle. So miss penalty 20 cycle, all this given miss penalty, hit time, miss rate is also given like I cache miss rate. There is no example for a D cache, so we don't have to find out average memory access time for a D cache as well. So only I cache. So it is 1 hit time plus 0.05, which is the miss rate, and 20, which is the miss penalties. It is 2 nanoseconds. Time is given in nanoseconds. We are going to find out in nanoseconds. Remember, 1 nanosecond clock means in 1 nanosecond we execute 1 clock. So in 2 nanoseconds we are going to execute 2 clocks, so 2 cycle per instruction. Using this formula, average memory access time, we are going to find out how many CPI we are going to need, how many cycle per instruction. Clear? So if that was like this, 2 nanosecond clock, what would be the answer in here? Please respond.
Yes, sir.
What would be the answer in here if the question was like 2 nanosecond clock? Then it would be 1 cycle per instruction, right? Please respond.
Yes, sir.
Okay, so for 1 nanosecond clock, it is 2 cycle per instruction. So this is the end of the lecture, and remember, this is your home assignment 2. I'm going to open this panel today, and there will be one more week to submit the assignment. Okay. So within the next week, actually, I'm not going to give you 1 week. This will be too much for you guys. Maybe less than that. Okay, I'm going to think about that. So this is the home assignment 2. Find out the answer of question B and C. Clear, everyone? Please respond.
Yes, sir.
Yes, sir.
Okay, now that your syllabus is finished, your final CT will be only this lecture, only memory organization. Final CT will be only on memory organization. Now, you guys please let me know whether you are going to give the class test on the next class, Sunday, or in the last class. I guess you better give the class test on Sunday.
স্যার
because
ওয়েডনেসডে হলে ভালো হয় স্যার।
because if you give the class test on Sunday, you are going to get at least a review for that on the Wednesday. At least you know your mistakes. If you see the paper, check the script. You don't see that, you don't know your mistakes, you don't learn from them. So I guess for your good, I'm going to stop the recording in here. No need for further recording.